So today we're talking about chi-squared, and this is how you write that, chi-squared. If you were to spell it out, it's C-H-I. So far in this class, we've been mainly looking at these two particular types of data. So just to review, these are our four main scales or levels of measurement. First is nominal scale, which has to do with categories. So if we're talking about males versus females or different ethnicities, things that can be grouped into categories, that's using the nominal scale. Ordinal scale ranks things, so if you had to say, your favorite TV shows from 1 to 10, or the order that people finished a race, first, second, third. If you ranked something on a Likert scale from disagree strongly to agree strongly, all of those are on our ordinal scale. The interval and ratio scale are very similar. There are very few interval scales. Ratio is much more common. This is the one we think of when we're actually measuring something. Like if we're talking about distance. 0 means there's no distance, and there is a consistent order and size of intervals between our numbers. So we've mainly been looking at things that have to do with interval and ratio scale, which SPSS collapses into that term scale. This doesn't mean that we haven't looked at things like gender differences, and we have, but when we've looked at them, we've also included another measure that was one of these other types of scales. So we haven't looked solely at categorical data yet, where all of our variables in a study are categorical. When that's the case, we use chi-squared tests. So chi-squared are used when all of our variables of interest are categorical or nominal. So our first example is looking at a survey of 120 restaurant customers. And our question is there a general preference for a specific type of drink? And we have 3 levels to this, which are wine, beer, and non-alcoholic. So this is a one-way classification chi-squared test, because we only have one variable of interest, which is drink type. And we use a chi-squared because these are categories that we can group people in, the type of drink. If you assigned a number to these, it wouldn't make sense, wine isn't 4 and beer is 8. Those are just representative of what they are. So if this is our question, our null hypothesis is that no, there is no general preference for a specific type of drink, or people are equally likely to choose any of the 3. So our null hypothesis is that customers are equally likely to prefer any type of drink, so the probabilities of choosing each type of drink are equal. So if there's no preference, people are just as likely to choose wine as beer as non-alcoholic. If that was the case, since we have 3 categories, we would expect 1/3 of the people to choose wine, 1/3 of the people to choose beer, and 1/3 of the people to choose non-alcoholic. So if we did our survey and we were looking at what people actually chose, this represents the data that we got. 18 people of our 120 chose wine, 54 chose beer, and 48 chose a non-alcoholic drink. And that adds up to our total of 120 people. So it appears that the majority prefers beer, but we have to ask, is this a reliable difference in the population of restaurant customers? So beer appears to be highest, and whereas wine is the lowest, but is this a significant difference that we see among these 3? Is there actually a preference for one of these versus the others? So what we do in our chi-square test is we compare our actual observed frequencies, which are these values here, with the frequencies we would expect to get if the null hypothesis were true. So remember, the null hypothesis, if this were true, we would expect equal numbers in all 3 of these because there would be no preference for one or the other. So given that we have 120 people, if there was no preference for any of these over the others, how many people would we expect to choose wine? Yeah, so if we just divide this by 3, we would expect 40 people to choose wine, we'd expect 40 people to choose beer, and 40 to choose a non-alcoholic. So it's just a third of the people would choose each of these because there's no preference for one or the other. So our chi-square test is comparing our actual observed values with our expected values if the null hypothesis is true. And again, this is just showing if we divide it by 3, we would expect 40 in each group. This is also called the goodness of fit test, and this is actually what it's referred to in the glossary in the Kulikin book. And the reason it's called this is because we're wondering how good or how well does our observed data fit our expected data. So does it match for our null hypothesis? And if it doesn't, that suggests that we have a significant difference, or that there is some preference or some difference among our group. This is the statistic we use to calculate our chi-squared test. So it's just another thing that we calculate, like if you were to calculate a t-value or an f-value, chi-squared, you'll end up with an actual value. Now remember, this symbol here means that we're going to be adding things up. And so that means we're going to do this for each of our categories and then add all of our categories up. So in this case, we have 3 categories. So O represents our observed frequency, or the actual number we got. E represents the expected number for that category. So for our first category, which is wine, we would take the number that chose wine, subtract the expected number if our null hypothesis was true, square that difference, and then divide by that expected value. Then we do the same thing for our next category, which is beer. So our expected value for beer, observed value minus expected value. Square it and divide by the expected value. And then, that should be down here. And then the same for the third one, just the same way. So then we'll have 3 numbers. This tells us we add them all up and we'll get some value for chi-squared. So we can actually do this. In this case, our expected values are the same for all 3 of our categories. It's going to be 40 for each of them. So this is however many chose wine, was 18, minus 40, which gives us negative 22. And that squared is 484. So negative 22 squared, 484. If we divide 484 by 40, that gives us our first one, 12.1. 54 minus 40, that'll be 14. If we square 14, we get 196. 196 divided by 40 is 4.9. And 48 minus 40 is 8. Square that and we get 64. 64 divided by 40 gives us 1.6. So since we have 3 groups, we'll have 3 terms. Add these 3 up and we get 18.6 is our chi-squared. So it's actually fairly similar when we're doing a chi-square test to kind of doing in format to doing a t-test, in that we get a t-value, then we need to determine whether that's a significant value or not. So we do that based on how many degrees of freedom we have. So the next step is figuring out how many degrees of freedom are there for this particular test. So to compute degrees of freedom for a one-way chi-squared, that's simply the number of groups or number of categories minus 1. So since we have wine, beer, and non-alcoholic, subtract 1 and we're left with 2. So we have 2 degrees of freedom. There's a table in the back of the book on page 662, and if you have a look at it, it's very similar and set up to the t-test table. And that at the top you have options for one-tailed or two-tailed tests. Of course, we're always going to use two-tailed, so you want to read the second line when you're looking at 0.05, 0.02 as your p-values and so on. Your degrees of freedom are listed down the left-hand side, so you want to find your particular degrees of freedom. In this case, it's 2. And then you can read across to see what your critical values are that we need to compare our calculated chi-squared value with to see if it's significant. So just so we can all see it, there's a online version. This one actually has quite a lot of information. It goes from 0.2 all the way to 0.001 with loads of columns in between. Of course, generally we'll start with our alpha level of 0.05. So you see this is an online version of the table, and so if we are interested in 2 degrees of freedom, we're going to be looking at this row. So for p equals 0.05, there's a value of 5.99. So we compare our chi-squared 18.6 with 5.99. If ours is bigger than this, it means it's significant at that level. The same as when we read the type t-test table. So it is significant at this level at 0.05. So we can go to the next column. Is 18.6 bigger than 9.21? Yes, so it's still significant at the 0.01 level. And is 18.6 greater than 13.82? Yes, so it is also significant at the 0.001 level. So we can say that p is less than 0.001 since our chi-square value is higher than this value. So this is just summing up our critical values for 2 degrees of freedom, either at alpha is 0.05 or 0.01. As you saw, you can go even further than that. We compare our obtained chi-square value with the critical value. If ours is bigger, then we reject the null hypothesis and say that it's significant. So we would reject the null hypothesis that, in this case, there's no preference. So this means there is a preference for drink. Now to do this in SPSS, I'm actually going to start out with a blank set of data so I can show you how you would set it up from scratch. So we need 2 columns of data. The first one I'm going to call frequency, which represents how many people are in each group. And that's going to be a scale variable, since 0 would mean 0 people are in the group, and counting from there. And our second variable is going to be whatever our variable of interest is, and so in this case I'm going to call it drink. So since we're doing a chi-squared and we're talking about a categorical set of data in what type of drink, we're going to make this a nominal variable. And I'm just going to label these so I know which groups are which. 1 is wine, 2 will be beer, and 3 is non-alcoholic. So under drink, we have 1 group for wine, 1 group for beer, 1 group for non-alcoholic, and then we need to say how many of each of these we have. So we have 18 in the wine group, 54 in the beer group, and 48 in the non-alcoholic group. Now, our data is set up properly now to do the analysis, but there's an important step you have to do in order to actually run it properly. So once we have it set up like this, this is essentially saying 18 number 1s, 54 number 2s, and 48 number 3s. So it's easier to set it up like this rather than to put 1, 1, 1, 1, 1, 1, 1, 18 times and so on, and have a really long string of data. So all we're doing is we're summarizing it for SPSS, but we need to tell SPSS that this is what we're doing. So to do that, we come up to this symbol that looks like scales, and this is called weight cases, and you select that. So it'll ask, you can either not weight cases, which is the standard, or weight cases by. And we want to weight cases by our frequency variable, which in this case is just frequency. So this is going to tell it we have this many of this category. And if you look at the bottom right hand corner here, it doesn't say anything right now, but once we click OK, you see it says weight on, so this tells you that the data has been weighted. So now it's going to treat it like you have 18 1s, 54 2s, and so on. Now to run our test, we go through Analyze, and for this chi-square test, the one-way classification, we go through non-parametric tests, legacy dialogues, and chi-square. And this is all up on this slide. Since we've already done what we needed to do with frequency, we weighted by it, we can ignore that variable. We're only interested in type of drink. So drink type, we move over to test variable list. We don't have to select for anything else. We just click OK, and it runs our analysis for us. So here it shows us our observed values, our expected values if the null hypothesis is true, and this last column is the residual, or 18 minus 40, 54 minus 40, and 48 minus 40. So this can come in useful if you're trying to check a chi-square by hand. This shows us our actual test statistic. We have our chi-square value of 18.6, which is what we calculated by hand. Our degrees of freedom is 2, and this asymptotic significance represents our p-value. I've noticed in exercise 2 that some people are still writing p equals 0.000 for this case. Remember, when it says 0, it doesn't mean that it's actually equal to 0. It's just so small that it's rounding. So instead of writing it like this, we would write it as p is less than 0.001. So we're saying it's so small that it's almost 0. To come up with our graph, we can just do this using our chart builder. We want a bar chart, and we want type of drink on the x-axis. Don't put anything in here, it'll automatically tell you how many. And if we display error bars for 95% confidence intervals, then this should give us the appropriate graph. So with our sample of 120 customers, there was a statistically significant difference in preference for the 3 types of drink available. And we know that because our p was less than 0.05. For a chi-square of 2 degrees of freedom is 18.6. P was less than 0.001. And we can see that beer was the most popular choice and wine was the least popular choice. Now this is a little similar to when we did a one-way ANOVA, where we know that there is a significant difference, but we can't necessarily say where the significant difference is just based on the chi-squared test. So as far as I know, there's not a test that we typically use to follow this up, but a general rule of thumb for figuring out which groups are significantly different from each other is by looking at your 95% confidence interval bars. So if the bars overlap, like they do between beer and non-alcoholic, that implies they're not statistically significantly different. So we could just as well have the numbers from this one and the numbers for this one, because these 2 confidence interval bars overlap. For wine, however, we see that neither of these confidence interval bars overlap with the one for wine, which suggests that wine is chosen significantly less times than either beer or non-alcoholic. So if they overlap, we can't say they're significantly different. If they don't overlap, this implies that they are significantly different. An important thing for doing a chi-square test is that we have to start with frequencies for our calculation. So we have to start with actual whole numbers or counts of numbers. So if you're given percentages or proportions instead, then you just have one extra step to do at the beginning, which is convert that to frequencies. So if we were told that of 120 restaurant customers, 15% preferred wine, 45% preferred beer, and 40% preferred non-alcoholic drinks, we can't actually do our chi-squared using percentages. So we simply have to calculate what is 15% of 120, 45% of 120, and 40% of 120. So you just take that 0.15, multiply it by the total number in your survey or in your sample, and that'll give you the number in that group. So here these are just the same values as we used in the example previous. So once you've obtained your frequencies, you just run it in the same way as we just did. Now the other type of chi-squared test is the 2-way classification. And it's called this because we have 2 variables of interest, and both of those variables are nominal variables, or have to do with categories. So we have two variables, and each of them has two or more levels to them. Our aim here is to determine whether there's an association between our two variables, and this is kind of similar to what we did when we were looking for interactions in ANOVAs. So does one of the variables depend on the level of the other variable? And this is also called a test of independence, because really we're testing, are our two variables independent from each other, or are they associated? So our null hypothesis is they are independent. There's no association between our two variables. And alternatively, our alternative hypothesis would be that they are related somehow. There's an association between them, and they're not independent of each other. So if we take our data from the previous example, where we have 18 who chose wine, 54 chose beer, and 48 chose non-alcoholic, and we split that, our total of 120 people, if we look at it as men versus women, or split it into our groups by gender, we can see we have 80 men in our sample, 40 women, and this breaks up how the men chose their drinks. So 8 men chose wine, 50 chose beer, and 2 chose non-alcoholic. 10 women chose wine, 4 chose beer, 26 chose non-alcoholic. Okay. So we're just breaking it up, so we have one categorical variable here with 2 levels, and one here with 3 levels. Now, as in our factorial ANOVA, when I mentioned we had marginal means, in this case we have something called marginal totals. So this column here represents the marginal totals for gender, which tells us we have 80 total men and 40 total women. If we add these numbers up, we would get our total number of 120. This bottom one is our marginal total for type of drink. So this tells us we have 18 who chose wine, 54 chose beer, 48 chose non-alcoholic. Again, if we add up these marginal totals, we would get 120. And these numbers are going to be important for us to figure out what the expected values based on the null hypothesis are for each of our 6 cells. So again, we're going to test it similarly to the one-way one, in that we want to see our numbers, how do those match up with the expected numbers if the null hypothesis was true. And in this case, the null hypothesis is that gender and type of drink have no association. Doesn't matter if you're men or women, that won't affect how you choose your drink. So our expected values are calculated by multiplying our row and column marginal totals together, then dividing by our overall total number in our sample. So, to find our expected value for men who drink wine, we're going to take the 18 from the number who drink wine, multiply that by 80, which is the total number of men, and divide it by 120, our overall total. So if we multiply this out and then divide by 12, we'll end up getting a value, 120, we end up getting a value of 12. So this is the value we would expect if there's no association between gender and drink type. For women, we would take 18, multiply that by the total number of women, 40, divide by the total number in our sample, which is 120. If we did that, we would get a value of 6. So we would expect, based on our numbers, for 6 women to choose wine if gender and drink type were not related or not associated. So this is just showing what we did there. And so if we were to do this for each of these 6 groups, then these are the values that we would expect to get. So for example, if they weren't related, we would expect 16 women to order non-alcoholic drinks, 18 women to order beer, and so on. So we compute this in the same way, except it's important to note that whereas in our first example, our 3 groups had the same expected values, they were all 40, here we have different expected values for each of our groups. So our first, if we just look at this one, we're going to use the same formula, observed minus expected squared divided by expected. So remember, we're going to do this, and we're going to do this 6 times now since we have 6 groups to add up. So for this first one, we're going to have observed is 8, subtract our expected, which is 12, and we'll get negative 4. If we square negative 4, we'll get 16, and divide that by 12, and we end up getting 1.33. So this represents this first one. You would do the same for 50 minus 36 squared divided by 36, 22 minus 32 squared, and so on. So that's where each of these 6 terms is coming from. If we actually put them all through the calculator and figure them out, these are the values we get. Again, we have 6 terms because we have 6 groups. Add them up in our chi-squared test and gives us 29.7. So this is our chi-squared value. Again, we need to figure out degrees of freedom. In this case, it's the number in one variable minus 1 times the number in the other variable minus 1. And by number, I mean number of levels. So the other way of thinking of it is if you have a table, the number of rows minus 1 times the number of columns minus 1 equals your degrees of freedom. So here we had 2 rows, so 2 minus 1. Multiply that by our 3 columns, minus 1, and we get 2 minus 1 is 1, times 3 minus 1 is 2, and we get 2 degrees of freedom. This is the same number as in our previous example, so when we look at the table, we're actually looking at the same row, so we have the same numbers that we're comparing to. 29.7 is obviously much bigger than 5.9 and 9.21. If we were to look at the third one, 13, whatever, 29.7 is higher than that as well. So we get that this is a significant chi-squared value. So since our observed value is higher than the critical value, we reject our null hypothesis that our 2 variables are independent of each other. So if we reject that they're independent, the other way of saying that is they are associated, or one depends on the other. To do this in SPSS, we do this a bit differently than we did the other one. So we add a 3rd column to represent gender, and 1 represents male, 2 represents female, wine is still 1, beer is 2, and non-alcoholic is 3. And we have frequency split, so for example, this means 22 men who chose non-alcoholic drinks. We see in the right-hand corner that the weight is already on, it's already been weighted by this frequency. So we can go ahead and do our chi-squared test. Remember, if we're doing a one-way, we go through the non-parametric option. If we're doing a two-way, we're going to go through descriptive statistics instead. So we choose descriptive statistics, and then we want to choose crosstabs. So this is what we're using to cross-tabulate our 2 variables. So again, we ignore frequency. We've already used it to weight our data. And it doesn't matter if you put drink as your rows or columns and gender as your rows or columns. It doesn't matter which way around you do it. You'll get the same statistical result. I'm just going to do it so that it matches what we have on the slides and the table that we had, which was we had our 3 drinks as our 3 columns, and male or female were our 2 rows. Now we need to go into statistics. So if we just left it at this, all it would do is it would give us a table showing the values. So we need to go into statistics and ask it to do a chi-square analysis for us. Also, if you leave it like this, it's only going to give us the observed values. So if you want the expected values to show up, you go in cells and you have to select for it expected values here. So once we've done that, we get our result, which is here, and these are the 2 boxes that we really want to look at. So again, if you didn't select for expected, we wouldn't get these expected values printed out in our output, it would just look like this with our observed values instead. And if we didn't select for chi-square, we wouldn't get this box at all. So in this case, we see 29.7, that's what we calculated by hand, 2 degrees of freedom, and again, p is less than 0.001, so it's significant, and this implies that our two variables are associated with each other. You'll notice we have two options. You can either report the Pearson chi-square or the likelihood ratio, just indicate which one you report. Generally, you're probably just as well sticking with the Pearson chi-square and reporting that. This just indicates that if we have large enough numbers, these two values will really end up being equivalent. It's kind of like with our t and our z values. If you have enough people, those will end up being about the same at some point. And we can graph this just using our chart builder and selecting by putting gender as the option to split our variable by. And to summarize, we'd say our sample of 120 restaurant customers, 80 of which were men, 40 of which were women. Their preferences for drinks were not independent of their gender, which implies that their choice of drink was associated with which gender they were. Our chi-square of 2 degrees of freedom is 29.7, p less than 0.001. And the most obvious gender difference, which we can see in our graph here, occurs for beer. So here the two intervals overlap, and here our two interval bars overlap. So we're not really seeing any significant difference in the wine or the non-alcoholic groups. However, here we see there's a huge difference between the women who chose beer and the men who chose beer. So the majority of men preferred beer, while only the smallest number of women preferred it. And we've got our Ryan Gosling guy here. So he says, "Hey girl, since I met you, I've violated my independence assumption." So this is just leading into our first assumption for chi-squared tests. So our independence assumption has two parts. So the first part is that participants shouldn't influence one another. So theoretically, whatever I choose to drink shouldn't affect what you choose to drink. Our example is not actually the best example for this because people do tend to kind of notice what other people are drinking and base their drinks slightly on that. But theoretically, my drink shouldn't influence your drink. And participants should contribute only once to the data set. So that means even if people ordered 3 drinks, you would only count them one time. So let's say the first time is their choice of drink and that's it. You can't count them more than once, you can't ask them more than once. So they can only contribute 1 point to your data set. We want to make sure that our data is fairly normal. So this means that we want our observed frequencies to be normally distributed around our expected frequency for those cells. So the way we determine whether we're meeting this assumption or not is we look for cells that have frequencies of less than 5. If it has 5 or more, it's okay. If it has less than 5, then we might be breaking that normality assumption. And if we generally have, depending on how many cells we have, let's say we had 1 which had less than 5, it might be okay. We really want to look out for cases where we have more than 20% of our cells have expected frequencies of less than 5. So if it represents less than 20%, it's okay. If it's more than 20%, that means we have to do something to kind of fix our data. So our solution to that problem is we can either collect more data, because as we get more people in our sample, our expected values will go up, or we can collapse categories in our data if collecting more data is not feasible. And we have an inclusion of non-occurrences assumption, which means that if somebody doesn't select something, they should also be included in the analysis as not selecting something. So you don't simply ignore them if they don't choose one of the choices, they would be included as a non-choice. So you can think of this as in terms of voting. So if you asked 100 people in Stirling if they'd vote SNP, 50 said yes and 50 said no. Ask in Glasgow 100 people, 75 said yes, 75 said no. You wouldn't do a one-way looking at 75 versus 50. You would have to include those extra people who said no. So you would actually have an analysis of 200 people, not just the 125 who said yes. And we have to use frequencies, so if you start with percentages or proportions, simply convert those to frequencies and then you'll have met this one. So this is an example where we have small expected counts, so this is going to be a problem for our normality assumption. So in this case, for men drinking wine, we see our number is much smaller here, only 36 people. So if we take 9 times 13, 9 minus 13, no, 9 times 13, and divide by 36, we would get 3.25 for this one. So already we have one cell which has less than 5, because remember we want these expected values to be at least 5. And if we did for women, it would be 9 times 23 divided by 36, which is 5.75, and so on. So if we calculated all of these are the expected frequencies we would get, and we can see here that we have 2 cells that have values less than 5. The rest of them are over 5. So we have to think, what percentage of our cells are these 2? So we have 2 out of 6, which works out to be 33.33%. So we can either collect more data or we can collapse across our categories in order to get rid of this problem. What we're going to do in this example is collapse our categories. So this means we're going to combine wine and beer to be an alcoholic versus non-alcoholic category. So we're simply going to combine these two together. So we'll change this to be 12 choosing alcoholic versus 1 non-alcoholic. And here 10 women choosing alcoholic versus 13 non-alcoholic. So this is what I mean by collapsing our data. We just add them together. So if we were to run it as originally done with our 3 different drink categories, we would see that at the bottom of our chi-square test, we get this notice that says 2 cells, 33.3%, have expected count less than 5. So this is telling us that we're over that 20% and we need to do something to change it so that we're less than 20%. And again, those are the problem cells. So as I said, if we collapse our data, then we'll have 12 versus 1 and 10 versus 13. And this means our expected values are all over 5. So we're not going to have a problem with that assumption. If we run it again, this is again using the crosstabs option in descriptives, and we'll see that we get our Pearson chi-square of 8.3, 1 degree of freedom since we have 2 by 2, so subtract 1 from each of those and multiply. And our p-value is 0.004, so it is significant that gender is related to drink type. Now the odds ratio is something that's gaining in popularity, and because it's a way of boiling down your analysis to one number to make sense of it. So this gives us a single number that summarizes the relationship between counts in a 2 by 2 table. So this wouldn't work if we were using wine, beer, and alcohol, because that would be a 3 level. But if we're just using the example we looked at, men and women versus alcoholic versus non-alcoholic, then we can calculate the odds ratio. And it's particularly an important thing that's used in epidemiological studies. So these are ones that are related to issues of health, transmission of disease, control of disease, things like that, where we're talking about the risk of illness. And the odds ratio is the way that we report our effect size for our chi-square test. So to actually calculate the odds ratio, we start by calculating the ratio at each level of one factor. Then we take those 2 ratios and divide them together to create 1 ratio. So to make sense of this, if we think of our men versus women, alcohol versus non-alcohol. So first we want to do it at each level of one factor. So for men, our ratio of alcohol to no alcohol was 12 who chose alcoholic, 1 chose non-alcoholic. If you divide 12 by 1, we get a ratio of 12. For our other level of the gender factor, women's ratio of alcoholic to non-alcoholic drinks, 10 shows alcoholic, 13 non-alcoholic. If you divide these, we get 0.769. So now we've done this first part. We've calculated a ratio for men, and we've calculated a ratio for women. Now the second part, we have to take these two ratios and form a ratio of them. So we just take the 12 from the men, divide it by the 0.769 by the women, and this gives us our odds ratio of 15.6. So what does this number 15.6 actually mean? Well, it means that it's a way of summarizing our information from our table. So we could say that men are 15.6 times more likely to prefer alcohol than women. This statement can be interpreted in two ways, to go back to our discourse analysis. So you could also interpret it as men prefer alcohol over women. They would rather have alcohol than have women, which is not necessarily what we're trying to get at, right? So to rephrase it, men are 15.6 times more likely than women to prefer alcohol. And alternatively, if somebody prefers alcohol, then they're 15.6 times more likely to be a man than a woman. This is also a symmetrical relationship. So what this means is we can also phrase it the other way around. So women are 15.6 times more likely to prefer non-alcoholic beverages than men are. We can also switch around the order of our ratios. So if we take the reciprocal, which simply means 1 divided by our odds ratio. So 1 divided by 15.6 works out to 0.064. So this is the same as if we had, instead of doing 12 divided by 7.69, whatever it was, instead of doing it men divided by women, if we did women divided by men, this is the value that we would get instead, 0.064. So we could say women are 0.064 times more likely than men to prefer alcohol versus non-alcohol. So since this is less than 1, we're actually saying they're less likely. I think this way is more confusing because we're talking in terms of less than 1. And to me, talking in whole numbers like 15.6 times makes more sense, which is why I think usually you would want to go for the one that makes intuitive sense. Now the odds ratio in a more serious example and with a more sensible sample size. So really odds ratios are generally used with samples that are very large. So in this case we have 22,071 people, and approximately half of them are on a regime of taking aspirin and the other half take a placebo. We want to know whether their treatment, aspirin or placebo, is related to whether they have a heart attack or they don't have a heart attack. So here we see our numbers. 104 who took aspirin had a heart attack, 189 who took placebo had a heart attack, and those who didn't. And we want to know whether these two things are related. So we do our crosstabs in statistics, and let's see, where's this one? In this case, I see that my weight is not on, so I'm going to weight it first by frequency. Otherwise, you'll get something that doesn't make sense. And want to go through descriptives and crosstabs. And disease I'll put as columns, treatment as rows. Again, it doesn't matter which way. Statistics, I want a chi-square statistic. And to get our odds ratio, we also want to select for risk under statistics. And if I want my expected frequencies, that's under under cells. So now, in addition to our table and our chi-squared result, we also get the risk estimate, which is includes our odds ratio here. So here we see our odds ratio is 0.546, and we have a significant chi-squared value. It's p less than 0.001, and since we can see that less people had heart attacks that took aspirin than took placebo, then this is telling us what that difference is like. So to interpret it, odds ratio of 0.546 means that you can almost halve your risk of having a heart attack by taking aspirin versus taking a placebo. So if we were to take the reciprocal, 1 divided by 0.546, this would be 1.83. So if you are taking placebo, you're 1.83 times more likely to have a heart attack than if you were taking aspirin. We have our confidence interval for that odds ratio, goes anywhere from slightly under 0.5 to slightly over 0.5. And we can note that it does not include 1. So 1 is what it would be if these were both equally likely to cause or not cause heart attacks, or help or not help heart attacks. So since 1 is not in this confidence interval, then we know that this is a significant odds ratio. So in our total sample of 22,071 people, there was a significant association between the treatment and outcome from our chi-square analysis, which is reported here. And as a note, odds ratio, as I mentioned, is really only appropriate with large sample sizes like we have here. So if you did it with the drinks example, it wouldn't really make as much sense. And we want to use it when the event we're talking about, for example, heart attack, is something that has a low prevalence or low probability, so something that affects less than 30% of our groups. And lastly, if you remember when we talked about Lucy, and if Lucy got a positive breast cancer scan, what are her actual chances of having breast cancer? In that case, it was often easier to think of in terms of actual frequencies. So instead of 0.0001, that would be maybe 1 in 1,000. So thinking in terms of actual numbers can be useful. And this absolute risk idea is similar to that. So it's a more transparent way of communicating our data to consider risk, which is what our odds ratio was referring to. So heart attacks for those who are given the placebo, 189 people out of 11,034 had a heart attack. So this works out to 0.01712 approximately. If we were to change this into whole numbers, that would be about 17 per 1,000. So that means for people on the placebo, about 17 people per 1,000 people had a heart attack. For those who took aspirin, 104 out of 11,037 had a heart attack, and this works out to, in whole numbers, 9.5 per 1,000. So, between 9 and 10 people for every 1,000 who were taking aspirin had a heart attack. So our absolute risk is simply the number in our placebo group minus the number in our aspirin group. How many less people are having heart attacks in the aspirin group? 7.5 per 1,000. So aspirin has an absolute risk reduction of 7.5 per 1,000. Might not seem like a lot, but if you figure 1 million people, if they were to take aspirin versus a placebo, this would potentially stop a lot of people from having a heart attack. And that wraps up our chi-square. Sorry, I went just a little bit over. And next time we'll talk about some other non-parametric tests. And apologies, but I don't have your exercise